Hello everyone, my name is Dr. Roshan Kumar. I am Assistant Professor in the Department of Electronics and Communication Engineering, SR University, Warangal. So let us come to my topics. Today topics the what is biasing in PN junction, types of biasing, forward bias, reverse bias, and IV characteristics and application. So biasing is a process, the process of applying external voltage to the semiconductor device in order to control its operations. It is mainly used in PN junction diode and transistors. By applying bias, we can control whether current flow or not and how much current by flow that is decided by biasing process. Why do you need biasing? So in a PN junction there is a depletion region and built-in potential. At equilibrium, no external voltage is applied and there is no net current flow. To make the device useful in circuit, we must apply an external voltage. In a PN junction, this application of external voltage is called biasing. Providing the application um, external voltage is called biasing. So there are two types of biasing in PN junction. First one is forward bias. In forward bias, the positive terminal of the battery is connected to the P side and the negative terminal of the battery is connected to the inside of the semiconductor materials. So what happens in forward bias? The external voltage reduce the built-in potential, the depletion region becomes thinner. Charge carriers can easily cross the junction and start flowing the current in the PN junction device. So, in a forward bias, the diode conduct electricity. Similarly, in the reverse bias, the positive terminal is connected to the inside of the battery and the negative terminal connected to the P side of the semiconductor. Why? So what happened here when connecting the inside or positive terminal battery and P side connected to the negative terminal of the battery, the external voltage cross increases the built-in potential. The depletion region becomes wider. So just a opposite to the forward bias, and forward bias when applying the external voltage, the depletion region thinner. But in case of reverse bias, when applying a reverse biasing in a PN junction, the depletion region become wider. So majority carrier can't cannot cross the junction, only a very small leakage current flow, so that in a reverse bias the diode block the currents. So similarly, biasing is also important in the transistor. Proper biasing set the operating point, ensure proper amplifications, prevent the distortion of the signal. Without correct biasing, a transistor will not function properly. So what is the importance of biasing? Biasing is important because it controls the current flow. It determines the operating region of a device. It enables switching, amplification. It ensures stable, reliable operations. In a simple word, biasing makes semiconductor device practical and useful in real circuits. So now let us discuss one by one. So there are here you can see type of biasing, forward bias. Forward bias, we can see that a diode symbols forward bias, positive terminal connected to the positive point of the battery, negative terminal connected to the negative point of the battery. In the similar in the reverse bias, that reverse polarities, that is positive terminal connected to the of n type of the semiconductors and negative terminal connected to the p types of the semiconductors. So the connections is that connecting were positive and negative for n type and p types, that is called forward bias. In a forward bias, external voltage reduce the potential barrier allowing to flow the currents. So that positive terminal in region, that external voltage oppose the built-in electric field of the junction. As a result, the barrier potential decreases. So what effect on depletion region for applying the forward bias? The For applying the forward bias, the built-in potential is reduced, the depletion region become thinner, the electric field cross the junction because of the barrier become smaller, charge carrier can cross the junction is more easily. So how movement of charge carrier when applying the forward bias in a PN junctions? When applying forward bias, electron from the inside move towards the p sides and holes from the p side move towards the inside. These carrier cross the junction and recombine. As a more carrier cross the junction, current start flowing through the device. This current is mainly due to the majority's charge carriers. And how current flow in PN junction by applying the forward bias. When applying the voltage access the threshold voltage from silicon about 0.7 volts, for germanium about 0.3 volts. So the diode begin to conduct heavily. The current increases rapidly with the small increasing the voltage. This is why the forward characteristics curve of the diode rise sharply after the cutting voltage. That cutting voltage is 0.7 for silicon, for 0.3 for germanium. Depending upon the materials, the cutting voltage will be different for now. So the energy band in energy band gap, the external voltage reduce banding, the energy barrier becomes smaller. Electron require less energy to move from conduction band of N side to P side. Thus, recombination increases and current flow. Practical importance when applying the forward bias. So forward bias is used in rectifier, light emitting diode operation, signal detection, power supply in the circuit. In LED, forward bias allow electron and hole recombination producing lights. So for cross the threshold voltage for 0.7 for silicon and 0.3 for germanium. Next is energy band gaps. How the energy band diagrams are shifted by applying the forward bias voltage. So by this explanation will help us to understand what happened inside the semiconductor at microscopic levels when forward bias voltage is applied. So we can just now quickly revision PN junction at equilibrium conditions. Before forward bias at equilibrium, the depletion region is formed and built-in potential exists. The conduction band and valence band near to the junction. The Fermi level is constant across the entire device. This banding representation the built-in electric field. Now let us see what's happening when we apply forward bias. Applying forward bias, the positive terminal is connected P type and negative terminal connected. The external voltage oppose the built-in electric field. As a result, the barrier potential decreases, depression region become narrow. So energy now imaging the energy band diagram when forward bias is applied, the energy barriers between the p-type and n-type region decreases. The banding reduced the potential barrier heights. We can see in pictures. So become a smaller, barrier height is a smaller. This means electron in the conduction band of the n-type side need less energy to cross into the p side. Similarly, holes from the p side can easily move into the n side so that reduced barriers allow charge carrier to cross the junction very easily. So Fermi level we have here in under forward bias, the device is no longer in equilibrium. Instead of one constant Fermi level, we now observe two quasi-Fermi level, one for electrons, one for holes. This indicates that the system is under external excitation. The separation between quasi-Fermi levels increase as a applied voltage increases. Means that when quasi-Fermi level will be shifted when applied voltage will be increases. So carrier movement in the energy bandgap explanation because of energy barrier is reduced, electron move from n region conduction band to p region valence band. Holes move for p region valence band to n region. These carrier recombine near the junction. This recombination leads to current flow in the device like LED. The recombination produces light. So, what are the important observation in forward bias energy band diagrams? Barrier height decreases, depletion with reduced band bending decreases, carrier injection increases, current increases exponentially. Even a small increase in forward voltage causes a larger increases in currents. So next is reverse bias. You can see in now is what happened in IV characteristics curve for applying the forward bias voltage. So now this we can see that equation with a diode current equation ID is equal to I naught e raised to power QV KT minus 1. ID is nothing but diode current, I naught is reverse saturation current, Q is charge of electron, K is Boltzmann constant, T is temperature, V is cut-in voltage, and so in IV characteristics, so what happened? So applying changing the voltage, that IV characteristics is shifted. The IV characteristics curve show the relation between applied voltage and resulting current in the diodes. So the curve, if you draw the graph, the horizontal axis represent voltage, applied voltage, vertical axis, that is y axis, represented current. In forward bias, the curve has three important regions. First region, below threshold voltage. Initially, when we apply a small voltage, very little current flow. The current is almost negligible. This is because the applied voltage is not sufficient to overcome the built-in potential. This region is sometimes called the cutting region. Means cutting region means now that is it's a point. After that point, that start flowing the current in the PN junction. Next is threshold or cutting voltage. As the applied voltage increased and reached a certain voltage for a silicon 0.7, for germanium PN junction 0.3, at this point the barrier potential is efficiently overcome. This voltage is called threshold voltage or cut-in voltage. After this point, current increases rapidly. Reason to rapid rise in current. Beyond this threshold voltage, a small increasing in voltage causes a large increases in current, because we can see that in diode current equation is exponentially increases. The current is increases exponentially. This is happen because the depletion region become very thin. Majority carrier cross the junction easily. Carrier injection increases significantly this region, so the diode is conducting very strongly. The diode current forward bias allow the diode equation current increases exponentially with the voltage. So what are the observation? A forward bias diode we have like a closed switch. After the threshold voltage, it is very low resistance in the conducting region. However, if the current become too high, the diode may overheated. This is why resistors are used in series to limit the currents. So below threshold voltage is very small current flow. At the threshold voltage, conduction beginning a start. Above threshold voltage, current increases exponentially. So the diode allow the current to flow easily for forward direction. Next is reverse bias. So in the reverse bias conditions, so positive terminal of battery connected to the n-type side and negative terminal of the battery is connected to the p-type semiconductor sides. So, so what happens when the external voltage support the built-in electric field of the junction? As a result, barrier potential increases. So what effect in depletion region when applying the reverse bias? So the built-in potential increase, the depletion region become wider, the electric field cross the junction become stronger because of the barrier becomes very larger, majority carriers cannot cross the junction. So, so what happen in moment of charge carrier when applying the reverse biasing in PN junction, electrons in the N region are pulled towards the positive terminals, holes in the P region are pulled towards the negative terminals. This movement pulls the majority carrier away from the junction. Therefore, no significant majority carriers current flow. So even though the majority carrier can't cross the junction, a very small current is still flow. That this current is due to the majority carrier is called the reverse saturation current. This current is very small, remain almost constant with increase the reverse bias voltage. Increasing increasing slightly, that reverse saturation current is increasing slightly with the temperatures. So what happen in breakdowns? If we keep the increasing the reverse voltage beyond that certain limit, breakdown occurs. There are two types of breakdown. Zener breakdown occur at the low reverse voltage in heavily doped junction. Another is avalanche breakdown occur at high reverse voltage due to impact ionization. During the breakdown, current increasing suddenly. If no limit, the diode may get damaged. Next is energy band explanation of reverse bias. After applying the reverse bias in the PN junction, this explanation to help us see what happened inside the semiconductor when reverse voltage is applied. So before applying the external voltage, a depletion region exists, a built-in potential present, the conduction band and the valence band near the junction. The Fermi level is constant across the diodes. Now let us see what changes when applying the reverse biasing voltage in energy band diagrams. So the positive terminals, so as barrier potential increases, depletion region become wider, the electric field cross the junction become very strong. So now imaging the energy band diagrams when reverse bias is applied, the banding increasing, the energy barriers becomes higher, the conduction bands on N types move further upwards relative to the p sides. This means electron in N region require much more energy to cross the p regions. Similarly, holes in the p-type region find it is very difficult to cross into N region. So majority carriers movement across the junction is blocked. So Fermi levels behavior under reverse bias, the junction is no longer equilibrium. Instead of the single constant Fermi levels, two quasi Fermi level appear one for electron, another for holes. The quasi-Fermi levels separate more as reverse voltage increases. This indicates that the system is under external excitation. So what happened in carrier movement when in the energy band diagram? So majority carrier are pushed away from the junction. The depletion region waned. Only minority carrier contributed to the currents. The current that flow is called reverse saturation current. This current is very small. So if voltage cross become very if reverse voltage become very high, the energy band bend sharply, the electric field becomes extremely strong, so breakdown may occur. This can be Zener breakdown and avalanche breakdown. At breakdown, current increases suddenly. So what is the observation in energy band diagram? In reverse bias, barrier height increases, depletion bit increases, band bending increases, majority carriers injection decreases, current remains very small until the breakdowns. So next is what happened in IV characteristics when applying the reverse bias voltage in the PN junction. The IV characteristics show the how current vary with the applied voltage in reverse bias. The behavior is very different from forward bias. So the so that reverse bias IV graph. If draw the graph, the horizontal axis represented voltage and vertical axis represented current. If reverse bias, the voltage is taken in the negative direction. The curve has two main regions. One is reverse saturation region, another is breakdown regions. So reverse saturation region means a small reverse voltage is applied, majority carrier pull away from the junctions. The depletion region becomes wider, almost no majority carrier flow. However, a very small current still flow due to the majority carriers. This small current is called reverse saturation currents. So as an important points, it is a very small magnitude. It is remain almost constant even if reverse voltage increases. It's increased with temperature. This region appear as a nearly flat line in the IV curve. In breakdown region, if the reverse voltage keeps increasing and reach the critical value, breakdown occur at breakdown voltage current increasing suddenly at sharply. The diode entered in breakdown region. There are two type of breakdown, Zener breakdown and avalanche breakdown. If current is no limit, the diode may get damaged. So what important observation is IV characteristics. Current is very small before breakdown. It is independent of applied voltage. It is temperature dependent. Breakdown cause sudden large current. So the normal operation reverse bias diode behave like a open switch. So that is basically in reverse bias. In practical importance, these are voltage regulator, protection of circuits, photodiode, rectifier, and Zener diode are especially designed to operate safe, safely in breakdown region. So next is differences. What are the differences between the forward bias and reverse bias. For a connections, P-type connected to the positive terminal battery and N-type connected to the negative terminal of battery. This is forward region, and P-type connected to the negative terminal of the battery and N-type connected to the positive terminal batteries, means that is for reverse bias region. Depletion region now features depletion region. In forward bias narrow and reverse bias is wider. Current flow, very high current flow after threshold voltage. In forward bias, very low leakage current. Barrier potential decreases in forward bias, but in case of reverse bias, barrier potential increases. Band diagram, bands bend downwards and bands bend upwards. Breakdown, there is no breakdown in forwards, but in reverse bias there is a two breakdown, Zener breakdown and avalanche breakdown. So thank you for watching my video. So